Welcome to Midnight Coding, everyone. Today we'll solve LeetCode question 684, redundant connection. This is a graph problem, and we'll be using union find algorithm to solve this problem. But before we continue, please like this video and subscribe to the channel, as it'll provide you with all the luck you need on your upcoming job interview. So if you're planning on getting into any of the fan companies, or if you have an upcoming interview, if you like this video, I promise you will get the offer. And also, it encourages me to keep making educational videos like this. This is a medium difficulty problem, but before we continue with our explanation and coding it up, I want to go over the concept and explain to you guys how exactly union find is helpful in this situation and how we can optimize union find. So let's jump into the explanation. Now let's think about how union find or disjoint set with rank works. In the beginning, all the nodes are going to have rank of 1. And when we connect two nodes, it doesn't really matter which one is going to become the parent node or the root node. So let's just say that I'm going to make this one the parent node. So this one is the parent node, and since we have made that one the parent node, let's update the rank. So the rank of this one is going to be 2, and this one is its child node, and this is the parent node now. So now when we connect this node over here with this node over here, now we ask, what's the parent of this node? So we can go up and we can see that the parent node of 1, this one over here, is 2, this red one. And we're gonna check the rank. So the rank of this is 2 and the rank of this one is 1. And we're gonna do the same thing with this node over here too, and we're gonna try to find its parent node. And how do we do that? Well, we know that this node is the parent of itself because of this connection. So we can just imagine that all the nodes starting out, they're going to be their own parents. So now, after we have done all that, we know that the parent of this node is this 2 as well. And we can just keep the rank as is. So let's do the same thing with the second half of this graph. So let's connect these two and let's make its rank 2, and let's connect these two. And now, what if you wanted to connect this one and this one? So if you wanted to make a connection between these two, first of all, we're gonna find its parent. So we're gonna go up, and we found its parent. Its parent is 2, and then we're gonna go up again, and this node's parent has a rank of 2 as well. So as I said again, if they're equals, it doesn't really matter. We can just connect these two like that, and then we can make the parent of this set to be this node, and then we will just update its rank as well. So to do these operations, we need two functions. We need a function called find, and we need a function called union, hence called union find. Basically, what happens is that you have two nodes. So this union function takes two arguments. So it takes node 1 and node 2. And this find function just takes one argument, which is node. Find goes to this node, makes itself up to the parent node. And union just tries to connect two nodes together. And here's what's so nice about union find or disjoint set is that, for example, if there was 3 nodes, we're gonna call union on these 2 nodes, and we're gonna try to find its parent, right? Let's just say for this example, they were their own parents. That's fine. And we're gonna do the same thing for these 2 nodes, and the parent is going to be this one over here. And now, if we try to connect these 2 nodes, we're going to call our find function over here on this node and on this node as well. But their parent is the same node. That means there's a cycle in this graph. So once we find this cycle, we can just return true, and we can just return the index or the value of these 2 nodes. So that's basically how we're going to use union find to solve this problem. Now let's think about what path compression is. Okay, so let's just say that we're looking at this node right here. We called our union function on 2 nodes, and let's just say this node over here happens to be this node over here. So its value is x. So the parent of x is y. But that's actually not true, because the parent of x is actually this one over here. Let's call it node z. So we're gonna say if x's parent equal to parent of x, because remember, this root node is going to point to itself, making it the root node. So when we go from x to y, y does not equal to its parent. So we're gonna make this is the current parent, and the parent of this also does not equal to this node over here. So we're gonna make our way up and up until we find the parent or root node. But in this example, you can see that we're going one by one, and we don't have to do that. We can do what's called path compression. Basically, what we're gonna say is that parent of x, this one over here, is currently this one. But we're gonna say parent of x is equal to parent of x. Parent of x right now is this node over here. So this node's parent, meaning this one over here. So we're making our progression faster by doing path compression. So here's a picture I found from Geeks for Geeks. And visually, it looks way better than what I just drew. So I'm just going to use this picture. So as you can see, the initial node or the root node is 9 over here. And these are all of its children nodes. Basically, what path compression does is that it turns this structure over here and makes it like this. So next time, if we have to access this 3 over here. So if this 3 wanted to go up, this can just go up instead of going from here to here to here and to here. So instead of doing that, it just makes it a really short path to follow. So that's just basically what path compression is. It's a really nice optimization technique, and it's gonna lower our time complexity. Now let's jump into the coding. All right, before we actually jump into the coding, I want to talk about how we are actually going to initialize the parent and the rank variables that we're going to create. So in the beginning, we want to make sure that a node points to itself. So this node's root will be itself. So we need that information to begin with. And how can we do that? Right? So all the information we've given is the edges. For example, this node has an edge to here, and this node has an edge to here. So what we're basically given is x, y, and x, z. And the length of our input is 2, but as you can see, there are 3 nodes. And when we initialize, basically what we're gonna say is that we're gonna take the length of our edges, the input variable we get, and then we're just gonna add 1 node to account for all the other nodes, because if we don't, we'll be missing out 1 node. So after that, when we get this, we're basically gonna say, so this node, it points to itself, this node points to itself, and this node points to itself. And we can do the same thing for rank. So the rank of this node is going to be 1, and 1 here as well, and 1 here again. So that's how we're going to initialize our parent and rank variables. So in Python, we're just going to use a dictionary, and in Go, we're just going to use an array to represent this relationship. And the next thing I want to talk about is the time complexity. So just to find function itself, it would be O of n. However, since we're using path compression, we can say that the time complexity is O log of n. So union, on the other hand, since we're using rank over here, let's just say that in theory, the operation should take log of n time because we're using path compression to use find. But the time complexity of disjoint set using path compression and rank together, the two optimization techniques, it actually comes down to O of amortized n, and that's the worst time complexity. So with that being said, now let's go into the coding. So here's the solution to the problem in Python. Although we can implement this code within the solution class and within the find redundant connection method or function, I'm going to implement this in another class. So in general, I think if we're with our interviewer, I think it's gonna give them a good impression that we're thinking in a more like object-oriented way. So I'm gonna define a class called Disjoint set, and then I'm going to initialize it. So in Python, we have the dunder init dunder method. So how we're gonna initialize this object is that we're just gonna get the number of nodes. And remember, from our drawing explanation, we can find the number of nodes from all the edges plus 1, but let's just define our disjoint set for now. So self.n is going to equal to n, and self.parent is going to be a dictionary, and it's going to say I is I maps to I for I in range of our in variable, the number of nodes. So what this is saying is that this node is the parent of this node. But since like in the beginning, we don't know whose parent is what, we're just gonna say that a node's parent is itself. So that's basically what it's saying. And then we're going to define our rank. So our rank is going to be very similar, but every node is going to start with rank of 1. Now let's define our find parent method. So I'll just say find, and it's going to take a node as an input. So we're going to say if n does not equal to, so in our disjoint set, like when we find a node, we are trying to find its root. What's the root? So that if this n equals to self parent at n, meaning that once we keep going up, we find the node that it equals to. So that's the root node. Here's another trick we talked about in our drawing explanation. So what we're gonna say is that self parent at n equals to self.find self.parent at n. So it's gonna keep iterating and calling this function until n equals to self.parent at n. And if it is, we can just return the root node. So now we've found our parent. Now we just gotta join them. So we can say, we can define a union function, and it's going to get 2 nodes. So n1 root and n2 root. We are interested in finding roots of these 2 nodes, and lucky for us, we just defined the find function. So we're just gonna say self.find at n1 and then self.find at n2. So now we know the root. We know that there is gonna be a redundant connection if and only if like 3 points to 2, 2 points to 1, and 1 points to 3. Like, you know that this edge 2 and 3 is going to make a redundant connection. So that's what we're interested in returning. What that means is that if 2's parent is 1 and 3's parent is also 1, n1 underscore root and n2 underscore root is both 1, that means there's a redundant connection and we can return false. So if n1 root equals to n2 root, then we just return false. Otherwise, we're going to join or union these 2 disjoint sets. So how we're going to do that? Obviously, we're going to use our rank dictionary that we have talked about in our drawing explanation. So what we're going to say is that if self.rank of n1 root, if it's greater than self.rank at n2 underscore root, if n1 has higher ranking than the n2, then the parent of n2 is going to be n1. So next time when you have to like union 2 things, we know which one goes where. And another case is just the opposite of it. So if the n2 root is greater than n1, then n1's parent is going to be n2. But what about if they are exactly the same? Well, in that case, it doesn't really matter which one goes to what. I'm just gonna say that n2's parent is going to be n1, and if this block of code executes, that means that we union those 2 sets and everything's good, so we can return true. And that's basically it for constructing this disjoint set class. Now what we're going to have to do is we're going to initialize our disjoint set object. I'm going to say this disjoint set is going to equal to disjoint set. So we need to provide the number of nodes. So the number of nodes is going to be length of edges plus 1, and then for source and destination in edges. So source and destination is obviously like from 1 to 2, 1 to 3, or 2 to 3. Since this is not a directed graph, it doesn't matter which one is source or destination, but I'm just naming my variable like this. Once we have done that, we can say if not disjoint set the union source and destination, meaning that if it does not return false, no, if it does not return true, right? So if it's not true, then we're going to just return the source and destination. And given the instructions, we know that there's going to be at least 1 redundant connection, so we don't have to return anything after this because we know that this return will get executed at some point. So now let's run the code to see if it works. Okay, it does. Now let's submit it, and it does. Okay, so this is how you implement disjoint set union find algorithm in Python. So if you've made this far into the video, thank you so much for watching, and if you liked it, please like the video and subscribe for eternal luck. And I hope you guys learned something new today, and if you guys have any questions, any LeetCode questions that you want me to cover, please leave a message in the comment section and I'll try to get it done as soon as I can. So I'll see you guys in the next one.